Stop one. Then let me know if you guys can see the slide.
I can see the first screen, not the slides just yet.
Let's see. Okay.
There we go. Perfect.
Okay, cool. So, all right. So let me get started. Thank you so much for coming here today. My name is Yuan. You can call me Lei. I am assistant professor from the Department of Psychology and Neuroscience. And I just recently became an affiliated faculty member of the computer science department. So that's one of the reasons I'm here today, to tell you about my research, and hopefully we can identify some common research interests. So to tell you a little bit about my lab, so I'm the PI of the DEL lab. So DEL stands for Development, Education, and Learning. So as the name implies, we study human learning and development with a focus on young children's cognitive development. I put a link for our lab website out there. So if you're interested in learning about the details about our research project, our team members, or any other related information, feel free to check it out. So we are a quite interdisciplinary team. We have students from psychology, computer science, mathematics, data science. We have students from design, the Alice Institute, education, and linguistics. So we're quite a melting pot of different fields. So to give you a sense on a very high level, the kind of interdisciplinary research that we do, our home domain is in cognitive psychology. So in a lot of ways, we study what makes us so smart as human beings, how do we process incoming information, represents knowledge, and solve problems. And of course, our focus is on cognitive development. So young children's thinking, how do they develop the different skills, and what are the possible learning mechanisms responsible for human intelligence? And one of the reasons I'm here is because our utilization of machine learning and AI models in our research. So we try to use different algorithms to simulate human learning with hope that we can better understanding its process and better predict in what context can we better promote those learning. A separate way that we use machine learning in our research is to use them as general data analysis tools, right? So decision trees, random forests, network analyses, use them to try to extract patterns from our research data. And then aside from the computational aspect, in terms of methodology, another unique aspect of our lab is that we also collect high density behavior data. So what I mean is we use eye tracking, visual audio recording. We're also designing a smart recording room where we're gonna track motion. So the idea there is to be able to connect those moment by moment sensory processes to our proposed learning mechanism in order to better understand how does that actually happen in the real time. And finally, a lot of our research have implications for education in terms of designing better teaching materials and foster better learning in young children. So this is on a very high level, the kind of different approaches we engage in. And I want to say, if during this talk, if you have any question, feel free to raise your hand or just unmute yourself and ask your questions, okay? So what I wanted to do today is to tell you a particular line of research as an example to show you how we use machine learning methods in the research of human learning. Okay. So humans are amazing learners, even the youngest members of our society. So for instance, here I have a toddler. So let's say one day she went to the park with her parents and they saw a really cute dog. And the mom may say, look at that, what a cute doggy. 2 days later, they went on a trail walk. They saw another dog, looks very different. The dad may say, look at that dog, he runs really fast. 1 week later, the this baby girl, this toddler girl may see the neighbor has a new puppy. And without much effort, she will be able to correctly infer that this creature belonged to the dog category, right? And this is just what typically developing 2 years old do on a daily basis. And this is why in the first several years of their life, children acquire thousands of words in their productive vocabulary. So let's think about what are the characteristics of this learning. This learning is highly generalizable. So based on some example, a learner can generalize this newly learned categories to never before seen examples. This learning is also based on very small data sets. So you don't need a lot of training data. So with 1 or 2 examples, human toddlers are capable of this learning. In the machine learning world, we typically call this few-shot learning to try to capture this idea of small training data sets, but broadly generalizable to a whole new category. It's known to be a difficult problem. So not only can human children learn object labels easily, they can also learn very sophisticated grammatical structures. So this sentence here may seem very simple, but it embodies this kind of hierarchical relational structure. And if you pile them on top of each other, it can get really complicated, right? But a typical 2, 3 years old have no problem understanding or produce this kind of sentence. And what is even more amazing is that they do so without people explicitly teach them the underlying grammatical structure. So you've never seen a parent say, this is a noun, this is a verb to a young child, right? So in the cognitive psychology field, we call this learning implicit statistical learning. So implicit in the sense that learners are not taught the underlying rule. They don't even need to explicitly represent these rules. Nevertheless, they can behave according to what is wrong and what is right under those different principles. Statistical learning refers to this ability of human learners to extract statistical regularity from their environmental input. And in this case, could be from the linguistic input they hear from their parents or other people in their lives. And this is also an example of a compositional system. So those are systems that have individual components and have rules and syntax with which you can put those components together, and in theory, in an infinite way, right? And there's a lot of examples in the machine learning world in which we try to capture this kind of learning. So examples include natural language processing, image captioning, visual question answering. So for the project I'm going to be talking about today, we're going to use the image captioning as a model to try to simulate this kind of human learning. So what I'm going to be talking about today it's not going to be on language per se. Rather, I'm going to focus on a different kind of compositional system, and that is the multi-digit number system. So if I were to show this number to a 4-year-old, he or she may think, oh, this is 5, 3, and 2. But you guys here wouldn't think so, right? You say, that's 532. And is further decomposable to 5 sets of 100, 3 sets of 10s, and 2 sets of 1s. And it's not just this number. You can give me any number, right? X, Y, Z, I can decompose it to its base 10 components. So this system is very much language-like. It has its own syntax. It's compositional and it's recursive. So you can give me a number and I can always generate a bigger number, right? It's highly generative. I want to say from the start that sometimes students with a machine learning background, when I mention multi-digit number system, they sometimes think about the MNIST data set, but it's not the same question really. So the MNIST data set is really about object recognition, right? Recognizing single digit number. Here, we're trying to see whether a learning system is capable of learning a number syntax, which represents this algebraic rule-like principle. Okay, any questions? Yep.
So does this match semantic, like in NLP, we heard of semantic trees and they are captured in a similar way. So is it similar to that? Right.
It is similar to that. But as you see, as I tell you more about the study, we're actually saying that they don't need to explicitly representing those syntax. they don't need to, don't need to build in a rule for them to understand it. They can extract those statistical regularities just based on input. Okay, so hopefully that will make more sense as I explain more. Okay, any other questions at this point? Okay, so I'm going to move on. And just to emphasize another point of why do we want to study this domain, is because this is a stumbling block for children's mathematical learning. So from decades of research, we know that this system is very hard for school-age children to learn. Even 3rd to 5th grade students struggle. And if they don't pass in this stage, they cannot move on to higher mathematics, right? They cannot do calculation and so on. And school teaching of the system typically focus on direct teaching of place value principles. So a teacher may directly tell the students that 100 is 10 cents of 10 and so on. This is almost analogous to direct teaching of grammatical structure to, say, second language learners, which we know doesn't always work well. And in the case of young children, they actually have never been taught grammar, right? But they nevertheless master the language system with those kind of implicit statistical learning mechanism. Okay. So in contrast to all of the difficulties that has been documented in the literature in terms of school-age children's learning, in a series of studies with large and nationally representative samples, my collaborators and I have actually found that a lot of preschoolers have this early implicit understanding of multi-digit numbers. So we use different kinds of tasks. In one of the tasks, we gave them 2 multi-digit numbers and we asked them to identify one by name. So point to which one is 36 in this case. On the left, I give you some example items that we used, and the graph here shows their general performance. And as you can see, even as young as age 3, as a group, young children perform significantly above chance, and their performance increases as they grow older. And in a second task, which we call the which is more task, we show them 2 multi-digit numbers and we ask them to identify which one has more. So which one is a numerically larger number. This one measures their understanding about the numerical quantities represented by multi-digit numbers. And again, you can see even at 3, they are above chance, and it gets even better over time. So not only do they have this early knowledge, it is also highly predictive to their future math learning. So this is a 3-year longitudinal study we have done across different cities in the United States. What we did is we measured their early number knowledge at kindergarten using these 2 tasks, which is in and which is more. And then we followed them for 2 years, 1st grade and 2nd grade. On the y-axis here, I'm showing you the 1st grade mathematics achievements measured using standardized tests that include skills such as their ability to do calculation problems. And what you see here is this beautiful correlation, highly correlated, right? Suggesting that this early, maybe not quite right knowledge might be important for later learning of precise base 10 principles. So an intriguing question is, where does this knowledge even come from in the first place? Based on a lot of research, we know that parents' number talks with young children is very rare. So they don't even talk about single-digit numbers that much, let alone multi-digit numbers. At least not in those research using methodologies that commonly we've seen in developmental research. Teachers are surprised about this as well. So when we tell them that we're trying to measure this kind of early knowledge and this, some of their students do know something about multi-digit numbers, they were quite surprised. So neither the parents nor the teachers kind of expected this early knowledge. So our question here is, what would be the learning mechanism possibly responsible for this early understanding of multi-digit numbers? And our proposal is that children can learn about the multi-digit system through the same implicit statistical learning algorithm that they use when they learn language. And when you think about our everyday life, we actually have lots of opportunities to be exposed to multi-digit numbers, right? Even though in most cases, the parents don't explain the place value principles. And those are also tend to be moments in our life that is hard to be captured by your typical experimental research methodologies. Okay. So our goal here is really to show a case of few-shot statistical learning of a compositional system. And here's our strategy. We're going to first test this in very young children, and we show the proof of concept that this system can be learned in this way. And second, we're going to test it in deep learning models to show that a domain general statistical learning algorithm can accomplish the same learning. And that might present further evidence that young children is using a similar mechanism when they acquire their early multi-digit number knowledge. Okay, we're trying to simulate children's learning. So for young children, what we did is we gave them several casual implicit learning activity. So one is this storybook reading, and I call it implicit. It's because we don't talk about principles. All they do is to read some books about numbers, and they read those number names, and they compare those numbers sometimes. So here, the images here shows you some example story. So for the training condition, they may see a book like this, and the story goes like, Johnny wants to save money to buy his favorite toys and food. Let's see what he wants to buy. He wants to buy a cake. It costs $40. He wants to buy a bike. It costs $60, and so on. For the control condition, we use an active control. So they played with exactly the same experimenter. They were in the same learning context of storybook reading. Everything is the same, except instead of learning about numbers, they learn about how to spell names for common objects. So here is the training and testing number. The training numbers are represented in red. And we present quite a sparse data set. So only 36 unique pairs of read and multi-digit numbers and their names. I say that's sparse because we are expecting children can extrapolate to the whole range of 1 to 9,999, okay, the whole range. And the testing number is represented in turquoise. As you can see, some of the numbers have been the children have saw during training, and some of the numbers are new, never before seen examples, and we use those to test generalization. And we use a pre and post test kind of design and use the same, which is in task, as I talked about before. And during testing, we use the novel items to test generalization. So basically what we found is compared to the control, only the training condition significantly improved their performance. And we have a little bit more kids in the training condition because we have different kinds of activities. Some are storybook reading, some they're just making multi-digit numbers with cards. Folks have questions?
I have one question.
Mm-hmm.
So in few-shot learning, in machine learning, we already use a pre-trained model. So my question is like, how does a human child do few-shot learning? Does the child have some pre-trained information in the form of, let's say, genetic information, and how does this manifest in the real world?
Right. That's a really good question. So I want you to think about what a 2-year-old know. What have a 2-year-old human child been exposed to? Is it a lot of data or a little data?
Little data.
A little data?
Little data, yeah. I mean.
So that really comes down to what do you consider as data, right? Mm-hmm. If you consider all of their visual input, they have lots of visual input of common objects, people, they have probably seen numbers, right? In calendars, clocks. So it's actually, from my perspective, they got tons of data, lots of data. In our lab, we also collect eye tracking data. Those are egocentric view. If you look at those egocentric view images, that's tons of data. Those I would consider as training data for human learners. right? So I agree, like when people talk about few-shot learning, and even when they relate to examples from cognitive psychology, is typically framed as, oh, it's based on sparse data. It's based on sparse data for the current problem that the experimenter is interested in. But from the learner's perspective, they actually bring a lot into this learning already. Okay.
Okay. Yeah.
And let me just add, when we model it using machine learning models, we also use a pre-trained model. So in a way that we're kind of trying to make it comparable to human children. So the model does not come in knowing nothing. The model is trained on some images on Google, so it has some basic ability to represent basic visual features. You got to have something like that to start with. Okay, I see more raised hands. Go ahead.
Sure. So just to follow up on that, I guess we could say that they have like 2 years of kind of unsupervised learning. And then as we go to make that formality, they start to get the official label and they can remember that for moving forward.
Yeah, I think you can think of it that way. It's an interesting question whether it's supervised or unsupervised learning.
Okay.
Right. Yeah. So what would you consider in the machine learning world? If you provide a label, then it's supervised learning, correct? Yeah. Then that would be the same for young children, right? If their parents talk about object names, if they talk about number names.
Okay.
They don't always correct them when they got it wrong. That is true. Right. And they do not always look at the thing you're talking about. So they may be learning the wrong pairings. That is also true.
Okay. Understood.
Yeah.
Awesome.
Good question. Yeah. Other question?
You also mentioned about the control group and training group. And in the control group, you don't tell them the numbers, but the actual words. So why we chose words in the control group? I think you're computing the confidence here, right? Between control group and training group, right? In the following figure.
Right. So in this kind of behavior experiment, we have several choices. So you can have your experimental condition, and you can have a control where they don't get this experience at all, right? They don't come in. I could adjust to test another group of children who are in the similar age group and provide a baseline, and that's fine. So what we are doing here is active control. So in a way, we're giving ourselves more stringent test. We say like, okay, it's not about the child had more experience with experimenter. So the child feel more comfortable. So maybe he or she can perform better because he just feel more comfortable with experimenter. We say, oh, we rule out that possibility because in the control, the children interact with experimenter as well, right? And similarly, you could say, maybe if you in the experimental condition, the children are more familiar with the testing environment or even to our lab environment, that could contribute to them doing better at our post-test. We're trying to rule out those competing hypotheses.
Oh, so that's the only purpose of the control test here.
That's
to
correct.
rule out those hypotheses. Okay,
yes,
makes sense.
Yeah, we're trying to keep everything the same except for that one thing we're really interested in.
Makes sense. And yeah, thank you.
Yeah. Good questions. Anyone else? All right. So overall, they have learned, what if we look at those novel items alone? So this is really testing generalization. So those are numbers they have never seen during the training. And again, we see a significant improvement suggesting that they're learning something about the number system, sort of like this latent structure, and they can generalize those relational structure into judging new numbers that follow similar rules, but they have never seen. Okay, so far we have accomplished our first goal. Now we're going to move on to our second goal, to simulate this learning using deep learning models. So whenever I try to choose a machine learning models to simulate human learning, I wanted to think about what learning processes of human learning that the model might be able to mimic. So let's look at our situation here. What we have is a learner and a teacher. The teacher provides number names, and the learners attend to the corresponding individual digits. So if I wanted to teach the number 49, When I say 40, I want the child to look at the digit 4. When I say 9, I want him to look at the digit 9, right? So we thought maybe image captioning is a good model to try to capture some of this learning process. And of course, image captioning is typically used to generate a description of a scene. So for instance, for this model, image captioning model might generate something like a child is reading numbers, something like that, right? So rather than giving the model images of people and objects, we give it images of multi-digit numbers like 124 here. And then we use your typical encoder decoder architecture. So the encoder is a CNN, which extracts visual features. And then we fed that into a decoder, which is LSTM network. And the output at each timestamp is the components in the number name. So 124, one at a time, very similar to when the child is learning, the child is hearing the number names one at a time, right? In the bottom, we have also illustrating attention mechanism. So we want the model to learn over time where in the image the model should prioritize for predicting the current label. So eventually, hopefully the model will learn when you produce 1, it should look at the digit 1. When you produce 20, it should focus on the digit 2 and so on. So I don't have time to go over the details. This paper is right on our lab website. So if you're interested, I would encourage you to go there and find out some detailed information. So I'm going to jump right into our results. Whenever you compare machine learning models, training performance and human learning, is tricky. They're not equal. So you have to think about different ways. If you read that paper, we used multiple different measures. I'm just going to show you one measure. They all tell us the same thing. I'm showing you one measure using the concept of edit distance. Basically, what you're seeing here is after 100 epochs, the model performs significantly better compared to 0 epochs when we just randomly initialize the model. So that's our baseline control. So that's just overall performance. We also wanted to look at error patterns. So for young children, not all items are created equal. So some items are easier than others. For instance, your single digit numbers is super easy to recognize, but multi-digit numbers with transpositions of items. So those are items like 36 versus 63. It's harder to distinguish, that's true. So in those cases, they perform the worst. There is a varied performance according to which type of items they were asked about. So we did the same analysis for model, and what you can see here is just basically show similar general pattern, suggesting to us that on an information level, maybe the model is capturing some of the processes similar to what children might engage in when they learn and when they solve those problems. We also look at the attention map produced by the model after training. So on the left, we have an example for the number 39. So as you can see, when the model produced the word 30, it quote unquote attend to 3. When it produced 9, it attends to 9. Similar for the 4054 on the right, when it produced the label 4000, it attends to 4. But when it produced the single digit 4, it attend to the 4 on the right. So in other words, our attention map shows that the model have learned the structural alignment between number names and written digits, suggesting that having this early implicit knowledge might direct attention to the correct component of the referred to number. And this is actually kind of important because it could potentially explain the high correlation that we saw previously. So it could be that really what allowed children with strong early multi-digit numbers to better learn math is that they can effectively direct their attention to the correct individual digits during teachers' lessons about place value. Okay? So we have recently received an SF grant to address specifically that question. So how multi-digit number names guide attention, memory, and learning of place value. So I just want to give you a flavor of the kind of research we do here. So for this particular project, we're going to use eye tracking to collect egocentric view data from our young learner. So this is the eye tracker that we modified specifically to work well with young children with smaller head. Typical eye tracker, you have two cameras, a scene camera positioned around the forehead, captures what's in front of the child, and an eye camera positioned a little bit below the eye through an angle here so you can capture the eye movements. So I'm going to show you the basic experimental setup and some of the pilot results. We did a pilot study with 8 kids. So on the left, we're going to see a child with high early knowledge. I want you to focus on where that child fixates, so which is indicated by the center of the crosshair. And so focus on where the child was looking in relation to the experimenter's verbal instruction. Okay, I will see if, tell me if you guys
So
can.
this number is
You
532.
hear okay?
What numbers did they have? Okay, let's count and grab 500. 100, 200. Can you count with me? 300, 400, 500. Good job. Go. Okay, let's look at the target again. How many tens did they have?
3.
Good job. Okay, let's count and grab 3 tens. 10, 20, 30. Good job. Can you put it down on the board?
It's 4.
Right. Let's look at our target again. How many ones did they have? 2. 1, 2. Good job. Okay. All right, Harrison. Good job. What number is that?
532.
Very good.
Okay, so he did a pretty good job. On the right, I'm going to show you a clip of kids with low early knowledge. Again, focus on where the kid was looking at in relation to the experimenter's instruction.
Number is 532. Can you tell me how many hundreds did they have? How many hundreds? It actually had 5 hundreds. Now let's count and grab 500. 100, 200, 300, 400, 500. Good job. Here you go. Very good. Let's look at our target card again. How many tens did they have? It actually have 3 tens. Okay, let's count and grab 3 tens. 10, 20, 30. Good job. Okay, now let's look at our target card. How many ones did they have? One. It has 2 ones. Let's count and grab 2 ones. 1, 2. All right. And you stack the cards together. Right down here. And you stack them together to make it look like our target card. You put it on top of each other. Right here.
Okay. So I hope you have noticed that the child with a low early knowledge, her eye movement just seems a little bit disorganized and less synchronized with experimenters, which is the teacher here, instruction, right? And it may seem like small delays here and there, but day in and day out, small difference in the speed and accuracy of eye movements may actually create large individual differences in the outcome of school learning over time. Right. So this is a project we're currently pursuing, collecting more data. One potential follow-up project idea is this idea of from naming to meaning. So from our research with young children, that training study I showed you, a really interesting result we got is that once we train these children on number names, they can generalize that knowledge to the judgment of magnitude, relative magnitude, but only for those numbers they got trained on, not for the numbers they didn't get trained on. So it's a generalization from one task to another task, but it seems like it's relying on the relational structure of the first task. So there's something really interesting, I think, to model in this case. Okay, so just want to mention that in case any of you are interested. So to further expand on this research program, we have also received a COC grant, and here is with my co-PI, Donna Gurare. sorry, I misspelled her name. It's Danna. So with Donna, we're really interested in two questions. The first one is to learn about how children learn to coordinate multiple representations. So here in the United States, children are first exposed to multi-digit numbers and place value during first grade. And they're typically, when they learn the system, they use a mathematical tool called base 10 blocks. And for those of you who are not familiar with this, basically it works by using a little small cube to represent the quantity of 1. And when you combine 10 of them together, you form a bar, and that's a unit of 10. So that corresponds to the decade place. And when you put 10 of the 10 together, it's a flat. It's 100, and you put 10 of 100 together, it's 1,000. So right here is a physical instantiation of the number 1,237. Okay, so in other countries or cultures, you may use different tools, for example, abacus, but all of them are supposed to teach you the coordination of multiple different systems. So in this case, we can construe this as coordinating the system of written number, the system of number words, and the system of physical quantities, right? So notice each of those systems has its own hierarchical relational structure. So what a learner need to do here is actually quite complicated, right? They need to understand the structure within each system, and they also have to be able to map the corresponding components from one system to the other system. And this is no small feat, okay? The students struggle with this. We know that for a fact. So we can construe this learning in different ways. So we can think about this maybe as a multimodal learning problem. So the learner is trying to coordinate, to learn the relational structure represented through different modalities, the written, the language name, the auditory, and the physical quantities. We can maybe also think of it as a meta-learning problem. So one interesting hypothesis would be if you first train children on the implicit number names, and then maybe they can better learn about how to associate those names and written numbers to physical quantities, sort of learn to learn, right? Learn the structure first, and then to transfer those structure to a new domain. Okay. And the second question we're interested in here is to see whether we can figure out the best teaching or learning regimen. No matter what domains you're trying to teach, there's multiple choices about the learning data you can present to the learner and in what order. So within the number system, you can think about, oh, maybe one hypothesis is you can present the small numbers first. So like numbers like 3, 10, 21, those are easy, versus your big numbers, the numbers in the hundreds, in the thousands range. But maybe perhaps it's not that case. Maybe the big numbers is good because the big numbers already have the small number components. So in a way, they are exposed to the system, the whole system compared to the smaller numbers, if that makes sense. You can have easy examples. So maybe numbers in the boundaries, the 20, 30, 100, compared to the more difficult examples like 39, 165, those have more components in them. Maybe they're more difficult. You can have regular numbers that follow the left to right reading order, or irregulars, like numbers in the teens range. I have one 4-year-old argue with me for the longest time that 13 should be rated as 3-1, not 1-3. That doesn't make any sense, right? From school teaching practice, what they do is they typically focus on the irregulars, the teens, a lot. So is that the best way to teach? We're not sure, right? Because if during early learning, all you learn is the irregulars, whereas for the majority of what you learn is the irregulars, then you're not learning the generalizable principle about the whole system. So we can frame this as a curriculum learning problem, right? Try to figure out what is the best teaching regimen. Okay, so those are some of the ongoing projects in our lab. Lastly, I just want to mention one potential future project I'm really excited about. So in terms of human learning, there's always been this tension from cognitive psychology between behaviorism and cognitivism, or constructivism, if you're from the learning science field. And it's basically this idea that, behaviorism, you're just learning associations of environmental input. typically those are described as implicit low level versus the cognitivism. You're learning high level representation of structure knowledge like grammatical structure, algebraic rules. Actually, some of the early questions capture this, right? Seems like low level versus this high level principled representation. But what I've shown you today and from many others research, we know that this implicit statistical learning is very important to later acquisition of precise place value principles, precise rules. Although these two kind of types of learning is typically pitted against each other in the literature, they're both important in real life learning. Ask any teachers, they will tell you that, right? So one way to resolve this tension is to use a mechanism that captures both kinds of learning. And one potential way to do that is with reinforcement learning with language. Okay, so reinforcement learning is something that we do every day. I go into the lecture today. Did you find the right classroom? Yes or no? Did you get the right answer? Yes or no? But sometimes the teacher's explanation is more elaborated. They use language as a way to do that. And language is very unique because it gives you this universal encoding mechanism, right? Can relate different experiences. The number 100, we can refer $100 or 100 bananas. They're quite different things, but they're all united within the same language. So some machine learning researchers already start to make this connection, but I feel like to really show the importance of this, to model, to understand human learning in general, we really need a collaboration from cognitive psychology to machine learning. And this line of research is really something that we wanted to further develop in the lab. It's very unspecified as of now, but if you're interested, please do let me know. So I have told you a lot about what we're doing in the lab. If you're interested in applying for independent study, currently we're only accepting independent study students, please prepare these materials, your CV, transcript, whether official and unofficial, both acceptable. And importantly, I would like you to write a 2-page research proposal that include these questions, this information. So a research question that you are interested in addressing and something related to us, hopefully, your proposed solution. And what do you think is the innovation? What's new about your solution? And especially from the computer science perspective and your past experience that makes you uniquely suited to pursue that research project. Email all of the materials to our lab email address, dellab@colorado.edu, and make sure you use this title, Master Students Independent Study Application. So we have a filter system, just go into that folder, okay? If you wanted to be considered for the spring semester, I set a deadline to be December 1st so that I have enough time to review your application and probably have a Zoom interview with you, okay? And all of this information is on our lab website. We have a tab called Master Students. So if you wanted to recall any of these details, you can go to our website. Okay, so I'm going to stop. It's been a long time and answer any questions you may have.
This was awesome. Thank you for presenting, Lei. I'm trying to come up with a question that seems particularly relevant and struggling, but I guess I am curious if there's been any attempt looking at different cultures approaches, and like you gave that example of abacus versus blocks, or anything in like languages, right? If we look at the Romance languages, they have different ways of handling numbers than English does. I'm just curious if that's been explored by you or some other people in the field.
Yes, that's a very good question. There's a long history in developmental psychology and education in general to look at cross-cultural, cross-linguistic differences in number learning. So one of the major results from that line of work is that children, say from Eastern culture, say the Chinese culture, they would learn language, the number of words earlier than children from, say, English-speaking country. And for the longest time, people are very cautious about what does that mean. So one proposal is because they have a more transparent naming system. So I'm a native Chinese speaker. So in 20 in Chinese is literally mean 210. So that is 210 versus in English, you kind of have to figure out what does 20 mean, right? However, one problem is you cannot separate the language influence with the culture influence, right? So it also could be that, I know this also firsthand in Chinese culture, for example, a lot of emphasis is put on education, right? There's kids spend more time working on their homeworks and the parents help and all of that. So we don't know really what's really causing their better performance. So what we are doing in the lab is to use our model to tease apart which hypothesis this is the case. Because if you use model, you can sort of get it around the culture problem, right? Your model don't distinguish. Your model is the model. So what we do is we feed the model with different number system. So could be just the English system or the Chinese system, and to see if the model would indeed learn faster or better with the Chinese numbers. If that's the case, then we can say, in terms of the information, on the information processing level, there's maybe an advantage in the language in some, the number words in some cultures than other cultures.
Interesting. Thanks.
Yeah.
Haley, I have one question. Thank you so much for presenting. It's very insightful. You talked about multimodal learning, where you are coordinating multiple representations. So I've been doing like this research using representational similarity analysis, which is called RSA, where you do analysis on different models and you relate so each of the models can be represented as a matrix, and you do try to find some correlation between different matrices and see if they are related.
Right.
So are you going in that approach, or how are you trying to relate different models of representations? Like the one that you mentioned, we can have physical methods, we can have numeric methods, and we can also have semantic trees where you represent languages. So how are you trying to model those things mathematically and computing the relations between them?
That's a really good question. So when you talk about RSA, it's a very common method in neuroscience.
Yeah.
Okay.
So yeah.
Yeah. So you can think of it, if you present a learner with one representation, it evoke brain representation or whatever in your model. It could be whatever the model's activation, right? And then you look at whether there's similarity between the different representations. I guess what we are seeing here is what we mean by represent. I'm not sure if the RSA will be able to capture the kind of relational structure we're talking about here, because it can look perceptually very different, right?
Yeah. So how are you trying to capture those representations? How are you trying to capture those models into some mathematical matrix or some other type of figure which you can able to relate with other device, or other measurement tool?
Right.
That's what I'm trying to.
Yeah. So let me tell you what we're doing right now. So what we're doing is to design an experiment for the model. So for some of the models, they were exposed to two type of mapping. So we're still using image captioning as a basic model. They were exposed to, if I show you a written number, I give you a label for the number name. And then different type of mapping is I show you a physical representation and the label is the same number name. Then we have two groups of control models. So one model was trained one type of model was trained only on one of the mapping, maybe the written numbers to number words. Another group of model were trained only on the physical representations and the number names. So our question essentially is to asking whether exposed models with multiple mappings, multiple representations can produce a better learner compared to if you are only exposed to one.
That makes sense. So you train the model with both the mappings, right?
Mm-hmm. Mm-hmm. Mm-hmm.
So how do you train it? First you train it with the number mapping and then you give it the physical mapping, or both the things are feeding simultaneously into the model?
We're exploring different ways. So that's related to the curriculum learning, right? How do you schedule it? Maybe maybe one is better than the other. So based on our behavior research with the kids, it seems to suggest that if you train on the number names, first and then
Okay.
do the model. That might be better. It's a
Okay,
possibility,
makes sense.
right?
Yeah.
But since we have models, we don't need to work with the kids. We can do whatever we want, right? We do
Yeah.
multiple different iterations, different type of training regimen, and that will help us to eliminate our hypothesis, right?
Thank you so much. Yeah, that makes a lot of sense. Yeah.
Yeah. Okay, anything else? Well, thank you all for coming, for your attention and listening to me. Your questions are excellent. So I'm hoping that I'll hear from some of you. Okay, and don't feel free to, if you have any further questions, drop me an email. Happy to answer them.
Thank you so much for doing this, Lei. We really appreciate it.
Yeah. Let me stop sharing. Losing my, okay.